All right, the paper we're jumping into today is called Thinking While Generating, or TWIG for short. And it really presents a massive architectural shift in how we approach complex text-to-image synthesis.
The core idea is simple, but it's really revolutionary. Yeah. Stop separating the thought process from the actual creation process.
Yeah.
TWIG is this new interleaved framework, and it's designed to inject textual reasoning during the visual generation loop, not before or after.
Right, because current models, they always seem to struggle with complex compositionality, long horizon coherence, all those nuanced instructions.
Exactly. They either think once and then generate blindly, or they generate the whole thing and then try to clean it up later.
TWIG just completely breaks that model.
It uses a unified multimodal model, a ULM, to iteratively plan a small segment, generate that bit of the image, critique what it just did, and then refine the prompt for the very next piece.
And it all happens in one single continuous trajectory. And what's so compelling is the progressive gain they show. Across 3 stages, zero shot, supervised fine-tuning, and then reinforcement learning TWIG just gets better and better.
It really validates this whole shift away from think before or think after.
To thinking while generating.
It's the key to making these systems truly context-aware in real time.
Okay, let's unpack this. I think we should start where the previous generation of models really hit a wall. We're talking about the limits of chain of thought methods.
That's right. For years, the reasoning part of visual generation has been stuck in one of 2 camps, and, both had some pretty big limitations.
The first one being think before generation, so pre-planning.
This is where you generate a whole fixed plan up front. Maybe it's a super detailed caption, maybe it's bounding boxes for a layout.
Right.
You hand that plan to the model, and it just goes. It's pretty good for global coherence, but the plan is totally static.
So no mid-course correction?
None. If the plan says a blue object and the model starts making a green one, it just it commits to the mistake.
It's that classic software problem, right? Great plan, zero runtime flexibility.
Exactly. And the second camp is think after generation or post-refinement.
This is where you make the full image first, then you have a powerful LMM critique it.
Right, you spot the errors, and then you iteratively fix them, usually with an image-to-image process.
That sounds better because you can actually fix things. But what's the catch? Why is it so costly?
Because you're running multiple, very expensive inference rounds on the full image for every little fix. If you need 3 rounds of refinement, you've basically paid for 4 full image generations.
Okay, that's inefficient.
And the critique is happening outside the main synthesis process. You're correcting the final output, not steering the process itself.
And this is where the inspiration for TWIG comes from. We've seen this kind of pattern inverted in visual understanding models.
Yeah, in LMMs. They use interleaved image text reasoning like zooming in or detecting an object to improve their own textual chain of thought.
And TWIG just flips that flow?
It's the first framework to successfully do it. You're weaving textual thoughts directly into the creation of the visual canvas as it unfolds.
It feels like such a foundational concept. And the authors made it clear that TWIG isn't, locked into one specific architecture.
Right. They use a single unified understanding generation LMM in their study Janus Pro, a 7B model, which is a great choice.
But the framework itself is broader.
Totally. You could have a coupled pipeline, like a diffusion model plus an LMM, or a single ULM. It works for diffusion. It works for autoregressive models.
And it's not just for text to image, right? They mention extending it to video to 3D.
It's basically a dynamic control mechanism for any long horizon generative task.
So let's get into the mechanics. TWIG maintains this single uninterrupted generative trajectory using 3 core components.
And it's all orchestrated by the ULM, which they sort of split into ULMU for understanding and ULMG for generation.
Component 1 is when to think, the scheduling.
Right, the ULMU has to decide when and where to stop and reason. You have to figure out how many reasoning points you need, Kay.
And what's fascinating here is the clash between what sounds good in theory versus what works in practice. Intuitively, you'd want an adaptive schedule. Think more about the complex parts, like a human face.
Yeah, but they found that current ULMs just aren't there yet. They struggle to generate stable adaptive schedules.
Well, what did they do?
They landed on a static schedule with K3. Just split the canvas into 3 parts: upper background, central content, and lower background.
Wait, really? So the super smart adaptive scheduling idea, the model just couldn't handle it?
Pretty much. The model basically said, nope, just give me 3 simple strips. It's a great example of where these multimodal models still hit a complexity ceiling Sometimes a simple heuristic is just more stable.
That makes sense. Okay, component 2. What's it? This is the reasoning content itself.
At each of those 3 stops, the UMU generates a textual thought, which they called cock. It acts as a localized subprompt just for that one region.
So it's the model's own self-guidance.
Exactly. And it's conditioned on the original prompt, any previous thoughts, and this is key, all the visual content it's already generated.
And that's how it maintains coherence. But this brings us to that clever technical trick. How does it pass that visual information without using a costly image-to-image model?
It passes it as a visual pre-context that's just appended to the end of the tech token sequence.
So it's treating the image it's already made as just more tokens.
Right, which allows the generation to continue as a text-to-image function, just with this extra visual context. It avoids breaking that continuous trajectory.
That is very clever, but doesn't that increase the context length a lot? I mean, could that become a scaling issue?
That's a great question, and it points to the limits of using a 7B model.
Right.
The authors get around it by keeping K at just 3, which keeps the token load manageable. For something like text-to-video, though, you'd absolutely need better tokenization or memory. But for T2I, K3 is the sweet spot.
Okay, and the third component is the safety net. How to refine the reflection part.
After each segment is generated, the UMU generates a reflection tuple.
Which contains what?
It's got a critic score, Super Sigger, from 0 to 100, based on things like color accuracy, object completeness, spatial relationships, and a revised subcaption, talk.
So the model scores itself against a checklist right there and then, and if the score is too low,
a self-correction gets triggered. And this is the big difference from think after. Instead of redoing the whole image, it only regenerates that one failed segment.
So it's a local fix.
A local fix guided by the revised thought. It stops small errors from turning into big ones. It saves time, maintains coherence. It's just a smarter way to build.
This framework is super ambitious, so let's talk about how they actually implemented it across the 3 routes they took.
Route 1 was the baseline, zero-shot prompting, or TWIG-ZS. They just wanted to see if the ULM could do this interleave reasoning straight out of the box.
With no extra training.
No extra training. They just very carefully crafted these interleave-aware prompts to force the model to follow the TWIG procedure.
And the results.
Surprisingly strong. TWIG-ZS blew the standard Janus Post 7B baseline out of the water, especially on compositional challenges.
I saw that. A 15-point boost on the complex metrics of the T2I CompBench++ day.
Which is a benchmark specifically designed to catch those tricky errors in object relationships and attribute binding.
So the framework itself is just fundamentally better, even if the model isn't trained for it.
And the ablations proved it. They confirmed K3 was optimal. They also showed that a single reflection round gave a huge boost.
But a second round didn't help.
Not in the zero-shot setting, no. It seems the model's built-in capacity for self-critique was pretty much maxed out after one go.
Okay, so zero shot proved the concept. The next step, naturally, is to give the model explicit examples. That brings us to route 2. Supervised Fine-Tuning, TWIG SFT.
Right. The goal here was to explicitly train the ULM on the TWIG workflow. They broke the process down into 9 supervised subtasks, thinking, reflection, and generation, and built a huge dataset for it, TWIG 50K.
And how they made that data is interesting in itself. They used models like GPT-4o to generate all the high-quality, stepwise subcaptions.
Yeah, to really teach the ULM how to think in this interleaved way. And SFT gave them reliable, modest gains over the zero-shot version.
But I think the most valuable outcome, at least for any engineer listening, was the stability.
Oh, absolutely. The SFT model dramatically reduced the standard deviation across different runs. You might trade a little bit of peak performance for something that's just reliable and predictable.
And there was a really counterintuitive insight about the data mix, right?
Yes. They found that a balanced mix of thinking and generation data was best. But when they gave the model too much reflection data,
training it to be a better critic,
it actually made the final results worse.
Why would that happen? Better reflection should be good.
The theory is that the ULM was already near its peak reflection ability from the zero-shot phase. Pushing more reflection data just diverted the learning resources away from where they were needed most.
Yeah.
Thinking and, actually generating.
So the model became a better critic, but a worse artist.
Something like that. It's a great reminder that for supervised learning, it's not just about data quantity, but about targeted utility.
That is a fantastic nuance. Okay, finally, they pushed it all the way with Route 3, reinforcement learning, TWIG RL.
This is where they tried to unlock all the remaining headroom. They used a custom strategy called TWIG GRPO.
And the key idea there was joint reinforcement.
Exactly. Instead of training each part separately, they reinforced all the reasoning, generation, and reflection passes at the same time, using a single shared reward that was calculated on the final image.
Which makes sure all the local steps are optimized for the global outcome. But with RL, the reward function is everything. You can't just use one metric or the model will hack it.
Precisely. To stop that, they had to build a composite reward model, an ensemble of 4 different components.
Okay, let's break them down. First, human preference score V2.
That's your global aesthetic reward. Does the image just look good to a person?
Second, object grounding scores. From something like Grounding Dino.
That makes sure the objects are actually there and in the right place. A cat on a table, not just near it.
Third, VQA consistency scores.
This one checks for instruction violations. If the prompt says the bird must be red, this score confirms it.
And fourth, LMM alignment scores.
Which gives a more holistic score on whether the overall vibe and abstract concepts of the prompt match the final image.
And with those 4 rewards guiding it, the result
were the biggest leap of all. Substantial gains over SFT. We're talking almost a 9-point jump on object relationship. It just confirmed there's so much potential left when you optimize the whole interleave policy end to end.
So when you look at the big picture, TWIG RRL, when you measure it on that T2I comp bench plus benchmark, it's getting scores that beat several leading models.
Even models with way more parameters like SDXL and LUX.1.
It's pretty strong evidence that this kind of sophisticated dynamic reasoning during synthesis is, for now, a better way to get compositional fidelity than just brute forcing it with a bigger model.
It's intelligence over brute force, yeah.
And for anyone listening who wants to implement this, the authors have laid out a really clear trade-off.
Absolutely. TWIG ZS is your cheap and cheerful option for a quick boost. TWIG SFT is what you use if you need stability. And if you're chasing state-of-the-art,
you invest in the RL.
Exactly.
So what does this all mean for the future? Where do we go from here?
Well, the immediate next step is getting past that K3 constraint. We need future ULMs that are strong enough to handle fully adaptive scheduling.
So the model itself decides when and where to think.
Right. If it can see a complex composition coming up and decide to pause and reason about it, that unlocks a whole new level of fidelity and efficiency.
And if we zoom out, TWIG really does integrate textual reasoning into the core synthesis loop. This isn't just about making better pictures anymore.
Which brings up a really interesting question for you to think about. We've seen how this interleaved reasoning plan, generate, critique, refine, improves visual generation. What happens if you apply this exact same framework to other complex long horizon tasks, like 3D model construction or autonomous robotics or even complex code generation? Could that continuous localized self-correction fundamentally transform how those systems perform?
That idea of real-time reflection steering production, that could be the next major step for large multimodal systems, forcing them to be accountable for their decisions at every single micro step of creation. It certainly gives us a blueprint for designing more reliable AI architects.